When building applications from the ground up, traditional software architecture usually starts out exactly like a massive single block of concrete. The user interface, the business logic, and the database access are tightly coupled into one unified deployable application. Early on, this tight coupling is an advantage. You write the code, test it, and deploy it as one cohesive unit. But bottlenecks emerge under load. If your payment processing feature gets swamped with traffic, you cannot just scale the payment feature. You have to duplicate the entire monolithic application. Scaling means multiplying the entire system. You spend resources deploying databases and UI layers just to keep one overloaded feature afloat, making the architecture financially and operationally unsustainable. To survive modern traffic demands, the only viable alternative is completely breaking that rigid, monolithic structure down into smaller pieces. We isolate each business capability into its own microservice. They act as a team of specialists, small, independently deployable services handling one specific job. If the payment service needs more processing power, engineering teams scale only the payment service. But splitting the code introduces a new problem. Instead of making a simple, instant function call in memory, these independent services now have to send data across a physical network. We solve the hardware scaling bottleneck, but we inherit the operational complexity of distributed network dependencies. If external clients try to talk directly to this new cluster of microservices, the system quickly degrades into chaos. First, it exposes the internal network topography. Every endpoint becomes a potential attack vector right on the public internet. Second, it forces the client application to know exactly where every service lives. If you change a backend route, you break the front-end application. Spring Cloud resolves this by inserting an API gateway between the client devices and the internal cluster. The gateway acts as the single point of entry. To the outside world, your complex architecture still looks like one cohesive unit. It centralizes cross-cutting concerns like security. Instead of putting authentication code in 50 different microservices, the gateway checks the JSON Web Token. Invalid requests are rejected at the door. Once authorized, the gateway takes the clean client request and forwards it to the exact internal location. It also acts as a physical shield. The gateway throttles abusive traffic spikes, protecting the backend from being overwhelmed. To run a secure distributed system, you have to decouple the external traffic from the internal network. The API gateway builds that perimeter. Inside that perimeter, the cloud environment is highly volatile. Containers spin up to handle load, and crash or spin down to save money. This means IP addresses are constantly changing. If your API gateway or a fellow microservice hard codes the IP address of a target, the connection breaks the second that target scales or restarts. To map this moving target, Spring Cloud relies on service discovery, commonly implemented with Eureka. It functions as the digital address book for the ecosystem. When a microservice boots up, it doesn't wait to be found. It automatically announces its current IP address to the Eureka Server. Now, instead of guessing IPs, the gateway asks Eureka for the exact current location of any required service before routing the request. This also enables client-side load balancing. Because Eureka knows exactly how many instances of a service are running, the gateway can distribute traffic evenly among them. Service discovery provides dynamic network awareness. The system tracks its own internal topography, allowing you to scale and replace nodes without manual configuration changes. In distributed systems, network latency and partial service failures are statistical inevitabilities. Consider a standard transaction. An order service needs to communicate with the payment service to finalize a checkout. If the payment service experiences a database lock, a response that usually takes 30 milliseconds suddenly takes 30 seconds. The order service is still accepting new user requests, opening a new active memory thread for every single call waiting on the slow payment service. The order service runs out of memory and crashes. The outage spreads from one slow database to the entire system. This is a cascading failure. To stop this contagion, we implement the circuit breaker pattern using libraries like Resilience 4J. The circuit breaker monitors failure rates. Once the payment service times out too many times, the circuit trips open, instantly blocking further requests. Instead of waiting and consuming threads, the open circuit immediately executes a predefined fallback. It serves cached data or returns a graceful error to the user. After a cooldown, the circuit enters a half-open state. It lets a single test request through. If the payment service has recovered, the circuit closes. Circuit breakers act as structural bulkheads. They ensure that a localized failure is isolated, protecting the wider network from a catastrophic collapse. When these components work together in a unified architecture, they tame the chaotic complexity of the distributed model. The API gateway secures the perimeter, authenticating clients and abstracting away the internal structure. Eureka maps the topography, constantly updating the live location of services as they scale up and down. Circuit breakers monitor the pathways, actively isolating latency before it spreads. When a live disaster strikes and a server dies, the circuit breaker trips immediately. The rest of the system remains functional, returning a clean error to the client via the gateway. An orchestration tool detects the dead node and provisions a brand new instance to replace it. The new service registers its IP with Eureka. The gateway discovers the new route, the circuit breaker closes, and full capacity is restored. Spring Cloud allows the infrastructure to identify, isolate, and replace failed components. The system maintains uptime by routing around outages and restoring capacity without manual intervention.